Welcome all. In today's lecture, Basics of SAR Data Processing. Myself Ashish Joshi. I am working as a scientist in Photogrammetric and Remote Sensing Department at IIRS Dehradun. In today's lecture, I will give the basic concepts on SAR data processing. Now, before giving the overview of data processing, I will brief you about the some radar and SAR concepts. So, what is radar? Radar is actually the device which transmits the microwave electromagnetic radiations or pulses towards a scene through a transmitter. So in this figure you can see this is a radar. It will transmit the pulses towards the target, and some of the electromagnetic radiations will backscatter towards the radar. Then these pulses interacts with the earth surface and backscatters toward the radar antenna receiver, and this radar will actually observe the strength of the signal and this distance r. Okay, so in the radar it will detect the two things. First is the detection and second is the range. So detection will come in the form of the backscatter energy in the images, and range is come as a mathematical number as a metadata in the radar file. So how this range is calculated? Range is calculated by simple formula of time is equals to distance upon speed. So this time delay is calculated like, because it is traveling two way, so this distance is 2r, and the speed of the electromagnetic wave is c, speed of the light. So the time delay is given by 2r by c. So from this formulation we can calculate the range is equals to c tau by 2. So in radar actually it will calculate this time very precisely. So in case of radar or in case of SAR, we are able to get a very precise range. So that's why this radar is called a ranging instrument. Okay. Now, what is synthetic aperture radar? So synthetic aperture radar is a imaging radar. So normal radar we cannot acquire the images, but using a some concept which is called the synthetic aperture. With the help of synthetic aperture, we can create a high resolution images of the particular area. So normally in remote sensing we are talking about images. Either it is an optical image or it is a thermal image or hyperspectral image. So in case of radar remote sensing, we are capturing the high resolution image by using the synthetic aperture concept. So what is SAR? SAR is a side looking radar system which makes a high resolution images of the earth surface. Continuous strips of the ground surface are illuminated to one side of the flight direction. Signal is recorded, and digital signal processing techniques in the ground are used to focus the image and obtain the high resolution image. The across track distance is called the range and the along track distance is called the azimuth. So in this diagram you can see this is a SAR, and SAR is a side looking system, and it is actually look either right or left side of a target area. So this is called the slant range, and what angle it is making with respect to the target, with respect to the nadir, then this angle is called the look angle. So what the range is making with respect to the nadir, this is called the look angle. So uh, in the case of synthetic aperture radar, it will actually transmit some pulses. So first pulse, second pulse, third pulse, and in this way the data is gathered. So this it is like a we can say normally in the optical like a push broom scanning. So it will just moving in this direction. This is called the flight direction, and it is sending some pulses and it is receiving some pulses. So that recorded pulses are written in a line by line manner. So in this way the data is gathered. So you can see in this image, this is called the SAR raw data. So in normally in the optical images, we are able to see some features in the optical image, either it is an optical or hyperspectral or thermal. We are able to see some features in the image, but in case of SAR images, we are not able to see any features. So what actually needed, we have to process the data. Okay, so that processing will be done on the ground using the signal processing technique to compress the signal and to have some we can visualize some features on the SAR image. So this is a SAR, a typical geometry of the SAR. So you can see there are different alphabets like A, B and C, and it will denote the different terminology in the SAR geometry. So here you can see this is the A. So A is the radar point platform. So here the radar or SAR is actually the position of the radar or SAR, and B is the flight direction. So B, you can see when the radar or SAR moves, so this is called the flight direction, or it is also called the azimuth direction. So the point directly perpendicular to the surface of the radar is called the nadir point. So C is the nadir point, and in here you can see there are two directions. So on the ground, actually what is the direction it is called, this is called the azimuth. It is similar to the flight direction. So what is the direction of the flight on the ground, it will form as a azimuth direction, and the direction where the it is transmitting the signal, that is called the range direction. So E is the range direction. So E is range, across track is called the range, and along track is called the azimuth. So in case of SAR, we are normally talking in terms of range and azimuth. So range is in the x direction and azimuth in the y direction. And F is the imaging swath. So when we calculate the numerical value of this, so this value is called the imaging swath. And G is called the far range. So that is the far point of the radar. So and this is called the near range, and this is called the far range. And this I is called the slant range. So mostly in SAR, the processing done in the slant range plane, so not in the ground range plane. So initially everything will be on this plane, which is this I. So this is called the slant range, and this plane is called the slant range plane. And J is the radar beam width. So this is the J is the full beam width. So in case of radar, it is similar to our torch, which we will use in our daily life, just like torch beam. So we can think of radar which is placed on the space, and it is illuminating the earth surface like a torch. So this is called the radar beam or the SAR beam. L is the energy pulses, which signals we are transmitting, and M is the echoes. So M is the echoes, means the backscatter signal. So this M is the backscatter signal, and this theta is the incident angle. So what is the incident angle? So this is the target plane. So what this range vector is making normal to the surface. So this is the normal to the surface. So what this range is making an angle with respect to the normal to the surface is called the incident angle. And what is the look angle? Look angle is the what the range is making with respect to the nadir line. So what is this angle? This is called the look angle. So when the surface is flat, so this look angle is equals to the incident angle when the we are considering the flat surface. But if we are considering the curved surface, then this incident angle will not be equal to the look angle. Okay, so these are the some of the geometrical parameters or geometrical terminology in case of SAR, which is basically the range, azimuth, incident angle, look angle, near range, far range, and like a incident angle. So these are some of the terminology you must know when we are interpretation when we do the interpretation of the SAR image. So basically we have the two resolution in SAR. Normally in optical image we are considering the single resolution, either the across track or along track. But in case of SAR, we have two resolution, one in the range direction, which is the x direction or cross track direction, and another is called the azimuth resolution, which is in the flight direction, or we can say y direction. So in case of SAR, as I have said, like it is in the raw data we are not able to see any feature. So for that actually we need some signal processing technique. So this signal processing technique actually we use like a pulse compression technique. So these pulse compression techniques are used in the range and azimuth direction to compress the SAR signal. So the fine range resolution is achieved by the pulse compression, and the fine azimuth resolution is achieved by using the synthetic aperture concept. The combination of these two principles enables to get a high resolution in both range and azimuth direction. Okay, so normally in SAR raw data we are not able to see any feature, but using the signal processing like pulse compression technique, we will compress the signal, or we can say we can focus the image to have we can see some features on the SAR image. So and normally in SAR it is an active sensor, so it will transmit the electromagnetic radiation, so we can say it as a pulse. Okay, so in normally in any electromagnetic wave we have some terms like wavelength, frequency, pulse width, pulse repeating frequency, pulse repeating interval, or sampling frequency. So wavelength, as you know, it is the distance between the two successive crusts in an electromagnetic wave, and the frequency is the number of crusts that passes through a fixed point in a given amount of time. So here you can see there is a relationship between the frequency and wavelength, which is called by C is equals to lambda nu. Lambda is the wavelength and nu is the frequency. C is the speed of light. So here we can say that the frequency is inversely proportional to the wavelength. So when we have the low frequency, then the wavelength will be higher, and when we have the high frequency, then we can have a wavelength will be lower. So in this image you can see this is the distance between the two successive crusts or troughs. It is called the wavelength. So in the low frequency you can see the wavelength is higher, and in the high frequency the wavelength is very much smaller. So how much is the duration of this pulse? That is called the pulse width or pulse duration. Now in case of SAR we are transmitting many pulses. So that is one term is called the pulse repeating frequency, and that is the number of pulses transmitted per second, means in 1 second how many number of pulses we are sending. So that is called the pulse repeating frequency. Okay, so we are when we design any SAR sensor, then we can we have this number also, means how many pulses we are transmitting in 1 second. So if the we can have the low PRF SAR and high PRF SAR also. So the complementary of pulse repeating frequency is the PRI. Okay, so PRI is given by what is the time duration between the two pulses when we are sending one pulse and first pulse and second pulse. So what is the time duration? So that is called the pulse repeating interval, and it is given by 1 by PRF. So we can talk in terms of either the PRF or PRI, means how many number of pulses we are sending in 1 second, or what is the time between the two pulses. So that is called the PRI. And next term is called the sampling frequency. The sampling frequency, the frequency at which the pulse is sampled for conversion of pulse from analog to digital. So in case of analog to digital conversion, we want to find number of samples. So a number of samples actually it is given by what is the sampling frequency into the pulse width. So how many number of samples in an SAR image, then it is given by Fs into tau, means as I have shown you this image. So here what is the length of this signal? So this is called the one pulse have some pulse duration. So how many number of pulses in this x direction? So that can be obtained by, if we know the sampling frequency, and we know this tau. When we multiply these two things, then we can get how many number of samples in the x direction. Okay, so that is called the sampling frequency. Now in case of SAR, we are having different level of products. So we can have a raw data products, so that is called the signal level data. From the raw data products, we will do some processing. Then we can get another level of product, which is called the slant range products. So slant range product is actually is also called the level 1 product. So there also there are two type. One is called the SLC and one is called the SLD. SLC is like, because SAR is an active sensor and it is transmitting the signal in a complex domain. So we receive the signal in a complex domain. Complex means we can have the real part also and the imaginary part also. So we have the single look complex image. Okay, so we have the real and imaginary part. So this single look complex product is very useful for because it has the phase information. This phase information is utilized in SAR application like polarimetry and interferometry. So in the interferometry, like if we want to have some deformation or any deformation study we want to study, then this phase information is quite useful. So for doing that application, we should use the single look SLC image. And if your application is for the visualization only, like if you want to see only the SAR image, then we can just see the single look detected product, which is an amplitude product, where the normally we can see as an image. So if you are not working in the phase domain, then we can just work on the single look detected product. So that is called the level 1 product or the sensor product. So any data, either it is a SAR data, hyperspectral data, or it is an optical data. So first product is the raw data. After that, it is called the sensor level product. Sensor level means in the sensor geometry. So that is called the level 1 product. So that level 1 product in SAR we are called as a slant range product. Okay. So another level of product is called the ground range product. So that I will explain in my subsequent slides. And after that we have the geocoded products. So one by one I will I will tell you what are different products and what are data processing is there, which is actually done to get the different products in the SAR. So you can see in SAR, first we have the raw data and we will apply some signal processing technique so that we can convert to the single look complex data, which is called the slant range products. And we will do some post processing to convert to the ground range product or geocoded ellipsoid corrected product or geocoded terrain corrected product. So from raw data, we will convert to the level 1, and doing some geometrical corrections, we can either make ground range product or ellipsoid corrected product or terrain corrected product. Okay. So first we will see how the SAR raw data look like. So you can see in case of SAR, as I told you, the SAR is a complex data. So in complex data, we are having the real part also and the imaginary part also. So in the SAR we are having the two bands. Normally in like optical we are having like red band, green band, blue band. In the same way, if we are getting the data of the SAR, we are the images are stored in like a bands. So we can have the real band and imaginary band. So we are having two images out of it. So if from the real and imaginary, we can calculate the amplitude. So amplitude is just like square root of real square plus imaginary square, and phase is given by tan inverse of imaginary by real. Okay, so in this way, from the complex data we can calculate the amplitude and phase. So amplitude is mostly used to visualize the image, and phase is used to do some application like polarimetry and interferometry. So now in case of raw data, how we can do the signal processing signal processing concepts. So there is one technique which is called the pulse compression. So in case of SAR, actually we are transmitting a linearly frequency modulated signal. So normally our electromagnetic signal wave signal is a form of single frequency. Okay, but in case of SAR we are having a special type of signal which is called the LFM signal, which is called the linear frequency modulated signal, or we can say an expanded pulse is sent. So here you can see how the signal of the SAR is looking like. So in case of normal signal, as I have told you in my earlier slide, so it has the fixed frequency. Okay, in this you can see it has the fixed frequency, but in case of linearly frequency modulated signal, you can see here the frequency is lower and here the frequency is higher, and it is an elongated pulse having the varying frequency. Now this type of signal is actually transmit in case of SAR, and on the ground as we will adopt one technique which is called the match filtering technique. What is the match filtering technique? In match filtering technique, we will multiply this signal with the complex conjugate of the signal and in the frequency domain. Okay, so when we receive any target 1 echo, means we are transmitting the signal and we are receiving this backscatter signal like this. Now this target 1 echo actually is actually multiplied with the complex conjugate. So when we multiply with the complex conjugate in the frequency domain, then the product is like this one. So you can see this expanded pulse is actually compressed, and it is compressed to very much high resolution. So this signal is now having a very much high resolution signal, and you can see like in target 2 also it is compressed. So if we are not doing any compression technique, this pulse compression technique, then we are not able to resolve these two targets separately. So normally in case of resolution, how resolution is defined in case of optical or SAR, means the ability of the sensor to distinguish two targets separately. Okay, so in case of SAR also, the pulse compression technique is used to compress the signal and to resolve the two targets separately. So once we apply this match filtering technique, we are compressing these signals and we are able to get a high resolution SAR images in the range direction. So there are different signal processing techniques actually we will apply. So in case of SAR, we will apply this pulse compression technique in the both in the range direction and azimuth direction. Okay, so in the azimuth direction, actually this LFM signal is formed by the synthetic aperture concept. In the range direction, what we are doing, in the range direction we are transmitting the LFM wave and using the pulse compression technique to compress the signal. But in case of azimuth direction, the with the motion of the SAR and due to the Doppler effect, a natural LFM is formed in the azimuth direction. So that LFM is also compressed by using the pulse compression technique. So we have to apply the pulse compression technique in the range direction also, in the azimuth direction also. And some of the terms which is basically used for raw data processing, which is called the range cell migration correction and azimuth compression. After adopting this all this principle, we are able to see some feature in an image. So all these things we will apply. So this algorithm is called the range Doppler algorithm. Okay, so in this algorithm we will apply the pulse compression technique in both in the range and azimuth direction, and after doing the raw data processing, you can see how the data look like. So you can see like L0, we are not able to see any feature on the image, but after compression, or we can say after focusing, we are able to see some feature on the image. Okay, so normally this level 0 processing is done by the space agency itself. Like if we are having our ISRO satellites, then in the ground station we will do this signal processing at the ground station only. Okay, so this type of processing is called the level 0 processing, in which the raw data is processed using the signal processing technique. So you can see how the, so you can see in this is the raw data and this is the process data EOS4. So EOS4 is actually our Indian SAR satellite, which is a follow one of reset one. So this is called the Earth Observation Satellite 4. Okay, so this was launched on 2022, yeah, and you can see the actual resolution of this image around 3 meter. So you can see how the raw data processing is applied on the SAR image, and we can focus the data. So this raw data processing we have done in our end, and we have generated the processed products at IIRS. So you can see how the raw data actually looking like in the SAR raw data image. So this pattern is actually the linearly frequency modulated signal, which I have shown you earlier. So this is called the chirp or LFM. Okay, so this actually pattern is actually due to the very much strong targets on the SAR image. So this type of pattern we can see in a SAR raw data, and using the signal processing concept we can compress this signal to have the features like this. So you can see these are the urban buildings here. So these urban, due to these urban buildings, we are getting this type of patterns, which is called the LFM signals on the SAR image. So this is the SAR raw data processing. Now we will talk to other products. After the raw data processing, we will get some products which is called the level 1 products, or we can say the slant range products. Okay, so what are the slant range products? So that is the level 1 product. So normally in SAR we are not able to see any features. So by using the signal processing techniques, we are doing the pulse compression in the range and azimuth direction, and generating a high resolution images. So that images which is generated after the raw data processing, it is called the slant range product. So normally the for the users we will get like slant range products or geocoded products. So I will discuss the slant range products and geocoded products both. So first we will discuss the slant range products. So you can see in this and normally in optical also we are getting the level 1 products, but in case of optical and SAR there is little bit difference due to the geometry of the SAR. Now you can see SAR is an active sensor. So the active sensor can image both in ascending node and descending node. Normally in optical sensor it is actually acquired the data in the descending node, but due to SAR is an active sensor, so it can image in the night also. Okay, so normally in the descending node the date, and it is due to the daytime, but in the ascending node in the night time also SAR can image the data. So SAR can image both in ascending node and descending node, and SAR can look in both the right and left direction. Okay, so most of the SAR has this capability to look either in the left direction or in case of the right direction. So you can see in the slant range image, it can be flipped in either range or azimuth direction or in the both the direction. Okay, so it can be either in the x direction or either the y direction or both in the both direction. So the slant range products are not geometrically corrected. Okay, so we have to do some geometrical correction on the slant range product. Okay, so when you get some slant range product, so you can see, and this is the actual, if you can see actual image or actual earth image. So this is called the range and this is called the azimuth. So when the SAR is acquiring this data, so if in ascending right mode means it is going from south to north like this direction and looking in this direction, this is the right direction. So you can see the SAR will acquire this data first and it will write in the top. Okay, so you can see this data is written here. So in this case you can see it is flipped in the azimuth direction or y direction. Okay, so in case of slant range product, if the product is acquired in ascending and right look, so the data is flipped in the azimuth direction. And if it is in the ascending left, so here you can see it is going from south to north and it is direction is like a left direction. So here you can see this data will come first. Okay, so here you can see if this data will come first. Okay, and you can see here the range is also flipped and azimuth is also flipped. So both in the range and azimuth direction the data is flipped. Actual the data is like this. Okay, but due to the acquisition geometry there is flipping either in the azimuth direction or in the range direction or in the both the direction. Now in case of the descending left there will be no flip of the data, and in case of the descending right there will be range flip. So you can see we can have a four images of the same area. Due to the acquisition geometry there is a flipping of the features, and this is actually not geometrically corrected image. Okay, so we will do some geometrical corrections of on the slant range product to get a level 2 products. Okay, so in the slant range product, the pixel direction is called the range and the scan direction is called the azimuth. So we can say the x direction is called the range and the scan direction is called the azimuth. And in the case of slant range product, we will have the SLC image also and SLD single look detected image also. In the SLC image, we are having the two files like real and imaginary files, but in case of detected we are having the single file and which is the amplitude. So how we are getting the amplitude? Simply square root of real square plus imaginary square, and it is geotagged. Geotagged means in this image we are having the information of latitude and longitude, but it is not projected to the on the ground. Okay, so only information is available, but it is not actually projected on the ground, or we can say any datum or on geographical coordinate system. Okay, so it is normal as an image and it is a normal L1 data with we are having some lat long information for the pixels, either grid by grid we are having, or we are having the four corner positions. So in the case of slant range product, we are having the pixel size, actually it is given by C by 2fs. So how much is the pixel size means what is the ground sampling distance between the two pixels. So this ground sampling distance, or we can say the pixel size, is given by the formula C by 2fs. Fs is the sampling frequency. So as I told you, sampling frequency is the when analog to digital we are converting, at which frequency we are converting from analog to digital. So that is called the sampling frequency. So if we want to find out the pixel size, that pixel size is given by the formula C by 2fs. Okay, and it is not a square pixel size. Okay, so we are having different pixel size in the range direction and different pixel size in the azimuth direction. Okay, so the in case of the slant range we are not having the square pixel size. Okay, so you can see in the case of slant range, so how this raw data is actually converted to the process data. So this is the level 0 data and this is called the level 1 data. So in case of slant range product also, if it is a single SLC image, so there are two type of product. One is called the complex product and there second is called the detected product. In the complex also we are having the real part and imaginary part. Okay, so in case of SLC we are having the two bands. One is called the real part and second is called the imaginary part, and we can calculate the amplitude like real square plus imaginary square. So after doing after calculating amplitude you can see the image. So here you can see in the SLC image we are not able to see anything, but in the amplitude image we are able to see the features. So this is the process product. Actually in raw data we are not able to see anything either in the real, imaginary or the amplitude product, but in case of the slant range product we can see the features if we can make an amplitude product. In this real and imaginary we are not able to see. So this real and imaginary only used to calculate the phase information, and as I already told that phase information is used in the polarimetric and interferometric application. So if your application to find out the subsidence or find out the what is the change coherent change detection type of, which depends on the phase value. Okay, like in case of SAR we are doing some special kind of change detection which is called the coherent change detection. So that time we will need the phase information, but if you are not doing that type of thing, if you are only observing the data, so we can just use this amplitude image and use like a backscatter information for the DN value. Now, normally the data is acquired in the slant range plane. So normally if this is the radar, so this line is called the slant range, and this plane containing this line is called the slant range plane. So in case of raw data processing, which I have told you in this uh, slide, when we are converting this thing, so all this thing actually done in the slant range plane. So data is also acquired in the slant range plane, and this processing also we are doing in the slant range plane. So our slant range product will be not actual the ground. So actual the ground is like this, but the data is projected in this in the sensor geometry is it is projected on this plane. Okay, so this because it is in the slant range plane, so there will be a geometrical distortions in the slant range product. So we can project this slant range product onto the ground by using this formula, like that ground pixel size equals to c by 2fs of sine theta. So if we are we can convert and use this formula to convert the slant pixel size to the ground pixel size, and this is a simple correction, geometrical correction we can apply to any slant range data. Simply we will divide by sine theta factor. Theta is the incident angle. So if we will divide that sine theta factor, then we are doing a minimal geometrical correction. Okay, so and that is called the ground range correction, or the image is called the ground range image. Okay, so you can see in this diagram, so this image is the slant range image, and after converting the to the ground range, so using this formula where the ground range is equals to slant range by sine theta, we are having the actual image. So here you can see the features are compressed. Okay, so because there is the actually it is not a square pixel size. So normally when we do this type of correction, we will make the square pixel size type of thing in the ground range, and you can see now the features actually appears better as compared to the slant range. So as I told you, in the slant range the geometry is not corrected. So if we know this angle theta angle and this range information, then with this formula we can do the minimal geometrical correction. So this is also not absolute correction. Okay, so absolute I will tell you later. So this is the minimal geometrical correction using the incident angle information by converting this one. So you can see now the data is looking better, and it is not compressed, and it is a square pixel size we are getting approximately. So this is the difference between the slant range and the ground range, where we will project the slant range image to the ground range. Okay, by using this conversion factor, and doing by this we are doing a little bit of geometrical correction in the SAR image. So here also you can see this is a slant range image, and this is the ground range image. Normally nowadays either the sensor will provide the data in the slant range or the ground range. So mostly we are getting, if you are and the sensor is giving the data, so either they will give the in the slant range or in the ground range. So if you are doing any polarimetric and interferometric applications, so they are actually given in the slant range geometry, SLC image type of thing. But if you are working on like detected image, only intensity information or amplitude information is required, then directly you can go to the ground range product. So like Sentinel-1 is a satellite which is giving the ground range product directly, and for interferometric application they are giving the SLC product. Okay, so either they will give the SLC or ground range. As per your requirement, you can use any of the product. Now as I told you, like ground range also, it is not fully geometrically corrected. It is just like a conversion factor from like slant range to the ground range by dividing with the factor of sine theta. Okay, but actual in the ground, if we want to compare our SAR image with other sensor like optical sensors or any hyperspectral sensor, then we have to do proper geometrical correction, and we have to project onto the ground. So for that, actually we have to do the geolocation. What is the geolocation? Geolocation is the we have to find the latitude and longitude of that information of that pixel, and using that latitude and longitude we will project our SAR image, either the slant range image or the ground range image, on the ground itself, like in the lat long geometry. Okay, so if we so what is the process? If we can find the latitude and longitude of this pixel, then we can project that pixel on the world geometry, or we can say geographical coordinate system. Okay, so the process of finding the latitude or longitude, it is called the SAR geolocation process. So in case of SAR geolocation, actually we are getting a very much precise range. As I told you, the SAR is a ranging instrument, and where we are getting directly the range, and it is because the range is calculated through the time delay, and time delay is very precise. So range is also very precise. So in case of SAR, if other issues will not be there, if the like state vector and other things are very much accurate, then SAR is providing a very precise geolocation. So first the SAR is measures the range, and second it is also measure the Doppler. Means as I told you, like SAR is a like a synthetic aperture, is used the synthetic aperture concept. So there is a Doppler in the azimuth direction, so it also measure the Doppler. Now using this range and Doppler information, we can get a very precise geolocation in case of SAR. So normally in case of SAR, the focusing, we have to estimate this range is very much precise, and Doppler we have to estimate from the image itself. Okay, now in case of optical image, actually there is the where the sensor is looking, so that look vector is actually calculated through roll, pitch and yaw. But that where the SAR is looking, it is actually estimated through the Doppler. Okay, so we are not dependent on roll, pitch, yaw, because roll, pitch, yaw have some sensor like sensor inaccuracies. So any error in roll, pitch, yaw will reflect on the optical images. So in case of optical, normally we will geolocate using the roll, pitch, yaw, where there will be the issues of inaccuracies. So we need the GCP, ground control point, to correct that inaccuracies. But in case of SAR, if our state vector, means satellite position state vector, is accurate, then we can just get a very precise range and Doppler, because we are estimating Doppler in a very precisely, because otherwise we are not able to see the image itself. So this image we are able to see because we are very much precisely estimating the Doppler value and range value. Then only we are able to focus the image. So in case of SAR, we are having very precise range and Doppler values. Using this range and Doppler value, we can make a SAR geolocation model. And because in case of SAR we are not using this roll, pitch, yaw, so in case of SAR we are getting a precise geolocation. If we are having all other parameters, okay, like if we are having the satellite X, Y, Z, its velocity and time stamping, all are correct, then in case of SAR we are having the very much precise. But in case of SAR, like if we are have imprecise position of the SAR, like if we are having not accurate GPS on the SAR satellite, then there will be issue in the XYZ values, then that error will reflect in the SAR geolocation process also. Okay, so that is the benefit of the SAR, because without any GCP also we can generate the automatically ortho product in case of SAR. So what is the SAR geolocation? Geolocation is the process of calculating the latitude and longitude of an image pixel. So for this image, what is the latitude and longitude that we have to calculate? So as in the SAR geolocation process, we are having mostly three equations. One is called the range equation, second is called the Doppler equation, and third is called the earth model equation. Okay, so when earth model is the what datum we are using, normally we are considering the earth as a ellipsoid, and normally we will consider earth surface as a WGS 84 datum. So we will consider earth as a ellipsoidal, and we have the range equation and Doppler equations. So all these three equations we will solve, and we will estimate the proper XYZ of a SAR image. Now once we know the pixel location of in a SAR image, like if in a pixel we are able to see, we are able to calculate the latitude and longitude of this, then that latitude and longitude will be used to project the image on the ground. So what is the SAR geocoding? SAR geocoding coding is the process of resampling the slant range image from SAR coordinate system to the geographical coordinate system. Means the data is acquired in case of SAR in the sensor geometry, like in the slant range plane. So from the slant range plane, we will calculate for a particular pixel what is the latitude and longitude, and that latitude and longitude information is used to project from sensor geometry to the geographical coordinate system. Okay, so that process is called the SAR geocoding. So there are two type of geocoding. So first is the earth, when the earth surface is considered as a smooth ellipsoid surface, there will be like uh, we are having a average height we are considering, like if you are having any terrain, and for particular terrain we are having an average height, like in case of Dehradun, we will, if we are considering a average height of Dehradun and we will do this SAR geocoding, then we can say like it is a geocoded ellipsoid correction. But for a precise thing, we have to find out the height for a particular pixel using the digital elevation model. So when we are doing the geocoding, when the dam is available, so that time we will use the geocoded terrain corrected products, or it is also called the ortho rectification. So geocoded ellipsoid correction means if we are projecting that lat long with an average height, that is called the ellipsoid correction. Means for a average ellipsoid we are doing the correction. But if we are considering the height of also of that pixel using the digital elevation model, then that is called the geocoded terrain corrected. So mostly we will use this type of product, GTC product only, because that is the ortho rectified product, and we can compare this product with other GIS products. Okay, like we can compare with the maps and with other raster images, like it is the optical image, or either hyperspectral or thermal image. Okay, now if the dam is not available, then only we will consider the geocoded ellipsoid correction. Like if we are having some real-time systems where we want to see the real-time data, then we will skip that part, and we will see like simply with the average height we can generate the products. Or if the dam is not available, like in case of sea, when like if it is a very much deep sea, there a dam is not available, so normally average height of the zero height we can just process the data and we can generate the ellipsoid corrected product. Or if there is a very much flat terrain, like a coastal area is there, so that case if we are applying the geocoded ellipsoid correction, then that will be also a good product. But mostly if the dam is available of any area, we will apply the geocoded terrain corrected products. So what is SAR geocoding? Actually what it will do, so this is the input space, like slant, it is a SAR slant range geometry. For that pixel we will find out the latitude and longitude, and we will put that pixel on the ground. Okay, so that resampling we have to do. So that type of thing, when we are projecting from one space to another space, like from the slant geometry space, which is called the input space, to the output space. Okay, so that is called the SAR geocoding. So that information actually is actually we are gathering from the SAR geolocation process. So SAR geolocation will give the latitude and longitude, and projecting from one space to another space, from input to output space. So here our input space is the SAR slant range, and here is the ground the earth geometry or map geometry we can say. So we can project from the SAR sensor geometry to the map geometry, or we can say like geographical coordinate system. So here how it can be done means here not actually we are not using the dam. So we will, for a particular image we are finding some grids. means we cannot find at each pixel. We will make some grids, and but at like 100 by 100 grid, at every 100 pixel we will find out the latitude and longitude, and from that grid we will establish the correspondence between input space and output space, and we will use some polynomial fitting type of thing, and using the average height and geolocation grid we can just rotate the image in the earth geometry. So you can see this is the actually the EOS image in the slant range, and after projecting you can see the this is the ellipsoid GEC product. So in this image you can see this is in the slant range geometry, and this is actual in the actual in the earth image. So this is the you can see this is the FRI. So this you can see as a FRI. Here the image is just inverted. Okay, so you can see the image. So after doing this one, and the image is in the proper geographical coordinate system, but here the terrain value is not used, so that you can see the geometrical distortions. So you may be knowing the layover shadow effect. So this layover and shadow effect you can see in this here also, and the features are not actually looking like a mountains. So it is actually the mountains, the Dehradun area, but in the SAR image, due to the geometrical distortion, this is not corrected in the ellipsoid correction. So I will tell you next what is the terrain correction. Okay, so you can see another image of that one. Okay, so this is, you can see the zoom portion at 3 meter. So this is, you can see the slant range image of the FRI in particular. So you can see the geometrical it is not corrected, and after doing the ellipsoid correction you can see the proper FRI image. Now in case of SAR, there is one term is called the relief displacement. Normally in optical there is a relief displacement, but in case of SAR there is very much high relief displacement, and due to that we are having the geometrical distortion like layover, shadow and foreshortening, and all this geometrical distortion is corrected by the terrain correction process. So you can see, and in case of normal relief displacement, in case of optical and SAR, so in case of optical the actually relief displacement is given by the h tan theta factor, but in case of SAR it is given by the h cot theta factor. So you can see if the angle is varying from 10 to 85, so you can see even on the 10-degree look angle also we are getting for a 100-meter mountain 567-meter displacement. Okay, but this relief displacement is more in case of near range, and as we are going far range the layover effect, or we can say relief displacement, is lesser. But in case of optical we can say how much is the relief displacement. For 10-degree we are having only 18 meter, and in case of optical we cannot give very much high look angle, so mostly 10 or 20 degrees. So mostly we are getting like 10 to 36 meter displacement for a 100-meter mountain. But in case of SAR, for a 100-meter mountain in a near range itself we are getting a 500-meter displacement. So you can see how much geometrically inaccuracies will be there in the SAR image due to the height values. That's why in case of SAR the terrain correction is the most important correction we have to apply for the slant range images. So you can see there are the three effects already in the last lecture. It has been covered: the layover, shadow and foreshortening effect, which is occur due to the ranging of the SAR, and it is a side looking. Okay, so due to the h cot theta factor we are having this layover, shadow and foreshortening effect in the SAR image. So all these effects the geometrically, if because you can see this pixel is written here. So using the terrain correction we can write this pixel again to this one. We cannot obtain the information back, but in a spatial domain means we can only correct the geometrical position of that pixel. Okay, so that is called the terrain correction. The information which are gone in the layover or foreshortening, that cannot be reverted back from a single SAR image. So that is only geometrically corrected, means we can just put the pixel using some using the dam and we will put the pixel here. So geometrically it is corrected, radiometric it is not corrected. So you can see in this is the US4 SAR image only. So you can see the layer 1 foreshortening in the SAR image. So you can see all these are the mountains here. So this is not appearing like a mountain in the SAR image. So now if we project this geocoded product on the dam, you can see these all are the actually the layer 1 foreshortening effect here. So this is the mountain, and all this information is actually compressed and written here. So you can see another example of the layover. So this is actually I have just grabbed our ellipsoid corrected, means using the average height we have corrected the data and put it on the dam. So this is the actual the mountain, but you can see the hilltop is coming here. So due to this because of the inaccuracies of the data, because the lat long is not correctly attached here. So if you are attaching on the correct dam, so it is not matching. So this is actually coming here. Okay, so if we are having the correct height, means correct product, then this should match with this dam product also. But due to this inaccuracies, you can see this hilltop is displaced. Now this all thing is corrected by the process is called the geocoded terrain correction algorithms, which is called the using the range Doppler algorithm, and using the dam we will do some corrections, and that corrections actually will make the ortho rectified image of the SAR data. So here you can see this is the geocoded ellipsoid corrected image. So you can see the hilltop is displayed here, but after doing the GTC correction, which is called the geocoded terrain correction and corrected product, so the image is actually this data is corrected actually. So you can, this is the Mount Fujiyama of Japan. So you can see after doing the this terrain correction, the properly the hilltop is placing here. So here what is this image? This is the geocoded ellipsoid corrected image. We are overlaying over the dam, because the dam is good, dam is precise, but our image is not precise. So this hilltop is displaced, but here both the things are precise, though both the things are actually matching, and the hilltop is getting up getting to the precise location. So you can see after doing the geocoded terrain correction how the image look like. All this are the layer and shadow things. So you can see this is the pulsar image. So this you can see the pulsar image we have done, and this is the Nova SAR 1 image actually. So in this Nova SAR image we have done the geometrical correction. So you can see this is the mountains, how in a slant range it is looking, and how it is you can see in the geocoded terrain corrected product. So you can see now the mountains is looking like a mountains. Okay, so here you cannot perceive like a mountains. So by doing this one you can perceive the valley and ridge in the SAR image. And when we grab this SAR image on the dam, you can see the 3D view of the SAR image also. Okay, so this is the Uttarakhand image of Kodwar region. Now I will just briefly tell you about our satellite, which is called the US4 satellite, which was launched on 14 February 2022 by PSLV C52, and it is a C-band synthetic aperture radar and a follow-on mission of the Reset 1. Okay, so earlier our satellite was Reset 1, which was launched on 2012, and after that this is a follow-on mission of the Reset 1, which is called the US4, which is a Earth observation satellite, which is a SAR satellite. Okay, so altitude is around 524.87 kilometers. So this is a typical geometry of our US4 satellites. So it is a side looking geometry with a near range like this one from 12 degree to at high look angle like 55 degree. This is called the far range. So from 12 degree to 55 degree it will image any area. So it can image any area in between that here. So it have different parameters, like it has the orbit is a sun synchronous orbit, and the frequency is the C-band frequency only. Antenna length is the like 6 meter in 2 meter, and it has the different polarization also. And the basically the it has the different resolutions based on the different modes. So in the last lecture you have maybe have the different modes like strip map, spotlight, and the SAR mode. So based on that mode, we have different resolutions images. So we are having a coarse resolution from 50 meter, which is called the CRS mode, and medium resolution, which is a 33 meter, and FRS1, which is a 3 meter, and high resolution spotlight, which is of very much high resolution of 1 meter. Okay, so these are different, means from a single SAR sensor we are having the multiple resolution using different modes like SAR mode, spotlight mode, and the SAR mode. Okay, and level of product, it is having the three level of product. We are having the raw product, also we are having the level 1, which is called the slant range product, and the level 2 product, which is called the terrain corrected product. Okay, and in the level 1, mostly level 1 is the SLC image, slant range product, and level 1B is the ground range product. So as I have explained in my lecture, we have different level of product like SLC image, ground range. So every satellite make this type of product, then maybe the nomenclature will be different, but the process is same only. Means it can have a slant range product, ground range product, and the either the ellipsoid corrected or terrain corrected. So here directly the terrain corrected products will be given. So if you are working on the polarimetry and interferometry, you have to use the single look SLC image. But if you are working on this level 2 product, you have to means if you are your aim is just like a classic like a visualization and do some type of observation mapping, so you can use like directly the level 2 product also. So here you can see the different SAR images. So this is the EOS4 raw data and how it is processed. So this is the Mumbai area only. So after the processing, so here we have processed this raw data. So after processing the raw data, how the image is looking like, we are able to see the images. So this is, you can see the bridge area. So you can see, because as you know in SAR that we are having like metallic objects, artificial object will be having very much high backscatter. So in the, you can see the bridge will have the backscatter, and the image is focused, then only we can see as a point target. If there are some issues in the data processing, then this image is not focused properly and it can be seen as a blur image. So you can see this is the normal slant range image only, and after doing the geocoded terrain correction, you can see the how the images. So you can see here are some small mountains in the Mumbai region. So you can see there is a some geometrical corrections happened. So this all are the mountain areas. This is the Dehradun image. So you can see this is the slant range image of the Dehradun. So here you can see how the mountains you are looking in the slant range image, but after doing the terrain correction, how the mountains are looking. So after doing this one, you can see the proper mountain shape, and you can perceive the valleys and ridges in the SAR image. Okay, so this is a Dehradun area image only. So you can see again this how this correction has been made. So this you can see the SAR image. So this is a ellipsoid correction where the only the average height has been used, but using the dam how the level 2 product is there. So when you receive any data, either raw data or L1 data, ground range product, SLC product, and the L2 product, so you have to see the data and you have to perceive what type of data it is. It is a level 2 data, level 2 it is a ellipsoid corrected or terrain corrected or SLC image. Okay, so we have to have some knowledge of the product type and product data also. So this is the Dehradun area only. So we have just grabbed that image, SAR image on the digital elevation model. So you can see this layer is actually you can see full spread over the mountain region, and due to the terrain correction process, and you can see proper mountains are forming after doing the terrain correction. And this is another image of the Kolkata region. So here the terrain corrected image you can see. So you can see this is the in the SAR image after the doing all the data processing from level 0, level 1, and terrain correction, how the data is looking like. So you can see this is the bridge, Howrah bridge of the in the SAR image, and this is the FRI you can see in the SAR image. So you can see this due to the high backscatter due to the building double bound scattering, you can see the FRI building having the high backscatter. And so you can see this image in the SAR image and this optical image. We can see how the different features are looking like. Okay, so this is the very much high backscatter we can see for the building, and for the vegetation we are having some medium level, and for the smooth surfaces we are having a very much low backscatter due to the specular reflections. This is another image of EOS4. You can see the how the bridge looking in the SAR image and in the optical image, and different features in SAR and optical, how it has been seen in the SAR and optical image. Okay, so that's all from my side. If you have any query, you can just raise your questions.